I have the honor of welcoming you to our fourth user meeting. It's a hybrid meeting, also to all the people remote. Welcome, happy that you join. Too bad you can't be here. Would be so nice to show you everything here. Good. I have a few slides prepared, taking you a bit of a journey from outside to inside. 10 years is the first time I'm saying that we're doing quantum technologies for 10 years, but it's true. It's in 2014 that we started actually with Andreas Wallraff here at ETH, seeing that quantum computing actually needs a bit different stuff from AWGs that are actually designed for telecommunications. So it started in a very close relationship with customers, and that's also how it continued. Stay close with the community. Why is this so important for us? Well, the most challenging thing for us is to detect new ideas, inventions, trends, and decide on whether they are going to propel science forwards and thereby be a business model for us. So we take these ideas and we develop them, crystallize them into commercial products, and thereby help the community forward. Now, the difficulty is deciding which trends are there to stay and which aren't. And I remember when we started, it was like, oh, we need HEMTs. Can't you do some HEMTs? And what do we do today? It's not HEMTs, it's tuple controller, like parametric amplification. So just an example of how things evolve over time and how important it is to stay at the forefront of science. Yeah, and it's the fourth user meeting, as you have seen here, to 2018, then in Grenoble, then in London, then came the Corona break. Then we had one in Munich at our new parent company, Rohde & Schwarz. Very nice event, and today it's the fourth. That's one way we interact, we build intimacy with the research community. Another way that is really at the core of our recipe for success is we have those collaboration projects. In those projects, we go into way more intimate collaborations. We share PhD students, we bring them in the company, and also the other way around. And we have them on quite an international level. The most recent one is the Super Moose in the ELK call. And anybody here participating in ELK, Super Moose? Yes. So here we have an example. Here we work on entangling two logical qubits. That's the goal here. And then in Switzerland, we have an Inno-Swiss project called Sherlock. How matching for error correction. Who's working in Sherlock? Anybody here? Can't believe it. Come on, it's next door. Okay, interesting. And then Munich QC, Q-Solid in Germany. Anybody here? Yes, awesome. I see 3 hands. And Super QLAN is actually all just finished, but I have another slide on it, so I decided to leave it on here. Here we work on distributed quantum computing. Open SuperQ plus, there must be somebody here. Yes, big project. Successor of the successful predecessor, Open SuperQ. Modular quantum computing. Nobody here. And Quantum Inspire, not sure. Any Delft is here, yes. Quantum Inspire, awesome project. Quantum computer in the cloud, you can actually go and use it over the web. So how do we see the community, the field evolving? And I say, how do we see? I realize you may see it differently, and maybe we can, and then when we have that, then that's very good, because then we can talk about this. So when I put the array of number of qubits, as we add more qubits, the challenges for the control side, also on the experiment protocol, theoretical side, certainly, but also on the control side, they change. And it's not a timeline. It's not that we move with time up from bottom to top. It's, yes, we move from bottom to top, but we don't stop working at the bottom. So for a few qubits, smaller systems, have a system that accelerates your progress, flexibility, have an architecture that will not impair whatever you want to do. There must not be constraints set by the control system architecture. And what we have is, we call it the centralized control, the star architecture. So there is no partitioning in the control system. And that actually holds up to also the next level, where we take it up, say, to 200, 500, maybe even 1,000 qubits, where you don't want to have a partition control system which would impose limitations. But when you move further up, the control system gets bigger, more components, and reliability becomes a huge topic. And Quantum Inspire, one example, where stuff just has to work 24/7, and if it doesn't, it's no longer acceptable. It's just breaking the project, and if you don't have dependable components, the system is not going to work. And finally, when we go to really large systems, we need to be tileable, as in tiles, distributed. And that holds both for the control software, for the quantum hardware, but also for the software. Because if the software just scales with the number of qubits, it's just going to be too slow. And there's also the time axis. We work in all these things. Those are our priorities. And it's also on the qubit technologies, fluxoniums, they're now kind of, I don't want to say mainstream, but the newcomers. There's new technologies coming up. And what's important is we focus on all these steps. It's not like we only care for the scaling. No, it's the entire thing. And this entire axis will continue for many years. Good. Then like to use this to switch over to the second part, which is more about us. So it's now 15, or is it close to 16? Actually, now it's going to be 16 years of Zurich Instruments. And so we're a spin-off of ETH. I'm one of the co-founders. We started the company, 3 of us. Today, we're more than 170 people, very international. I think it's actually more than 30 nations. Headquarters just next door, like there? No, there we are. And we'll go over there, but we're international. Why do we have to be so international? Well, we need this customer intimacy. So distributors for us, okay, sometimes I don't want to say they're useless. They're not. We need them. But the support for a quantum computing control user cannot be done by a distributor. Thus, we have offices in China, America, Germany, Korea, France, Japan, because we need this closeness for supporting our customers. And then since 2021, that's now 2.5 years, we are part of Rohde & Schwarz. And so far, this has been a success story. And we are still here, like standalone. We're a standalone case. So the Zurich Instruments brand continues. And our job in the Rohde & Schwarz family is to take care of the quantum and scientific community. And what it adds to us is now we have access to all this R&D and technology. We can make ASICs, and we can truly also tackle the scaling challenges when it goes to thousands of qubits. This photo was taken at our 15th anniversary, which we flew everybody in here. It was an awesome event. Good. Now, some success stories. I selected a few as an example on what we've achieved and where we could make a small dent. And one of these fields is quantum startups. So as a quantum startup, those are really bold folks raising money to build a highly experimental technology, IQM Atlantic Quantum. Both of them, they use Zurich Instruments control systems, and then at least that part is taken care of. Atlantic Quantum, most recent example, is started about 1 or 2 years ago, working on fluxoniums, and they are fully trusting on a Zurich Instruments control system, which of course is especially how should I say, nice, since there's former Keysight people in the team. That was a very nice, and they carefully evaluated it and chose us. I was incredibly happy about that. Another example, a bit like Quantum Inspire, we have at Berkeley at AQT, where the control system is actually on the internet, not publicly accessible, but yet there's a kind of like a community of people using the system remotely. And that's also run by Zurich Instruments, really high-end system, good qubits, nice package. To reach the reliability to get where stuff works 24/7 is an extra challenge, and we've achieved it at multiple places. Yeah, reliability. It's easily said, but what does it mean, and where are the challenges? As an example, I have 2 examples here on that slide. I'd like to mention this distributed system where we have a pitch and catch system. So here's this Airbus 330, 52 meters wingspan as an example of the physical expanse that we can cover. So in the center, we have our control system. At the ends, we have our 2 cryostats. And so you could build a quantum computing center with distributed bridges across that distance, and that works. Here's an example for a pitch and catch experiment where we emit a photon and then we catch it on the other side. And as a second example for stability, this is a measurement of the jitter over 2 weeks. And it's the only measurement of this kind I've seen. I've never seen any measurement that was done over 2 weeks. Temperature stability and all that. And what we see here is standard deviation is less than 20 picoseconds, and it's just stable for 2 weeks. And these measurements you have to do repeatedly in order to stay on that very high level of reliability. Good. Then a final example about variational eigensolvers. To do these experiments where you actually simulate quantum chemistry in a useful way, there's a long way there. And once you are there, the challenges change a bit. Now, in this example, we compute the distance in a hydrogen molecule, H2. And it's an iterative algorithm. And to run this thing in useful speed, you have to close the loop. And to accelerate that, there's a lot of optimizations you can do in the system. So what we've done here is we can exchange the waveforms without changing the sequence. So it runs, we rapidly compute the new waveforms, exchange the waveforms, and go for the next iteration. And unless you do this in like fast, your system will just drift away. Yeah, so that is my final example. What do we focus on today? Well, it's those projects that I've shown really at the core. If you are not yet there, but you would be interested to do something, today's the day to start the discussion. We really like these things. Next generation technologies, what's coming up, what are the trends, where do we have to add features, develop things. But also on the scaling size, reduce size, complexity, bring down the cost per qubit, more automation, speed up of software, and of course, add features. We're very open. Our Lab1Q is Apache license. It's based in Python, but to have even more third-party software inside, Qiskit already supported through Chasm, bring it even closer. And there are so many more other community-based software frameworks. Add them, be open, bring them into closer to our system. Quantum error correction, big topic. You will hear more about this. And with this, I'd like to thank you. Thank you, everybody, for coming over. Great to have you here. And I wish us all a wonderful day.